So I've drawn an arbitrary triangle over here that we will assume is not an equilateral triangle. And let's draw some of the interesting properties of this triangle. So let's first start with the perpendicular bisectors. So let's say this is the midpoint of this side right over there. So let me draw a little bit closer to the midpoint. It looks like right about there. So this length is equal to this length right over here. And so let me draw a perpendicular bisector. So a perpendicular bisector would look something like that for that side. Now let me do it on this side. So just trying to eyeball it. This looks roughly like the midpoint. So this length is going to be equal to this length. And then once again, let me draw a perpendicular bisector. So it's going to go at a 90-degree angle. I can draw a straighter line than that. So that looks pretty good. And it is perpendicular. And then you can imagine I will do it with this side, with side AB. So that looks like the midpoint. This length is going to be equal to that length right over there. And then if we draw a perpendicular, my best attempt to draw this, it looks something like that. And we've already learned that these three lines will definitely intersect in a unique point right over there, which we call the circumcenter. So let me write it. So this right over there is our circumcenter. This is nothing new. Circumcenter. Now let's draw the medians. So the medians go from each of the vertices to the midpoint of the opposite side. So let me draw. So this is a median. This is a median. This is a median. And then this is, and all the errors in my drawing will start to become apparent now that I'm trying to do multiple things with it. But we know all of the medians intersect at the centroid. So this right over here is the centroid. Now let's draw the altitudes of this triangle. So let's draw the altitude. So I'm going to drop a perpendicular right over here. This is one altitude. I will draw another altitude. So remember, it's just going to go down like this. Draw another altitude. It looks something like that. And then I can draw another altitude from this side. And we know it's going to intersect at this unique point right over here. So I'll try to draw it as neatly as I can. And this is going to be perpendicular, although the way I've drawn it doesn't necessarily look that way. And we know that this thing right over here is called an orthocenter. Orthocenter. Now, the whole reason why I'm doing this, and this is frankly kind of a mind-boggling idea, it's neat enough that each of these points even exist, that if three altitudes will intersect in one point, that the three medians intersect in one point, and they have all these neat properties, and that the three perpendicular bisectors intersect in one point. That by itself is neat enough. But what's really neat, and it's maybe not completely apparent by the way I drew it, because I just drew it freehand, is that these 3 points will definitely be on the same line. If this was an equilateral triangle, they would actually be the same point. But if for any other triangle, there will be different points, and they will be on the same line, which is just kind of crazy, because obviously 2 points define a line, but 3 points being on the same line is kind of a, it seems like a very unlikely thing if you were to just guess it. And I'm just going to try to draw it as best as I can. If you were to draw this with a straight-edged ruler, it would come out a lot cleaner. But all 3 points sit on this unique line that, it seems something special or magical about it. And because it's something special or magical, there's one famous mathematician who tends to get all of the most special and mathematical things named after him, because he's the guy who's really explored these things. And we call this the Euler line. Euler line. And I say that Leonard Euler, that doesn't look, well, it looks like enter. Well, I think you get the idea. Let me write Euler. Leonard Euler, the Euler line. I say that he gets all of the cool and magical, mystical things named after him because he's also responsible for Euler's identity, which is e to the I pi is equal to -1. And we prove this in the calculus playlist. And if none of this makes any sense to you, don't worry. We're only in geometry right now. But he gets to have all the... This is a magical thing because e comes out of compound interest and growth and decay, exponential growth and decay. I squared is -1. It seems this very bizarre imaginary number. Pi is the ratio of the circumference of a circle to its diameter, and -1 is well -1. And so Euler showed that there's a lot of reason to believe that these these 4 numbers that come from all of these different weird realities of the world are connected in this very tight way. And he also showed that these special points are all on the same line, which tells us something kind of crazy and mystical about our reality. And if that is not enough for you, if you take the midpoint on the Euler line between the orthocenter, and I'm not going to prove it here, I'm just going to give you a little bit of a tidbit of it. If you take the midpoint between the orthocenter and the circumcenter, so let's take this, so I'm going to try to look at it roughly. So it looks like it's right about there. So this length is going to be equal to this length right over here. This point that sits on the Euler line is going to be the center of something called the 9-point circle, which intersects this triangle at 9 points. And we'll see this kind of 9 interesting points. So let me label that as well. So it's not even, it's cool enough that these 3 special points are on the Euler line, but there's actually 4 special points. And actually there's a few more than that are kind of interesting. So that orange point right over there is the center of the 9-point circle. And maybe I'll do another video just on that. So anyway, hopefully you found that kind of interesting.